Hello and welcome to video 6 of my ISM project series. If you haven't watched the previous videos, please go ahead and watch them. They provide some really important context. So an overview of this video is that I'll be covering some key concepts in quantum mechanics by looking at some different experiments. Namely, we'll be looking at the measurement problem. And I'll be using the simulation from last video. And again, if you want to follow along or just mess around with the website, here's a link. So I'm on the website and I have created an experiment. And let's click start. And then we instantly see an interesting result pop up. In the third analyzer, we see that it records both spin up and spin down particles. But when we go back to the original particle beam, it originates from a spin up portion of the first analyzer. This is interesting. Let's go deeper into this. So if we break down the outputs of each analyzer, we see that the output of the first analyzer, we have spin up and spin down, but let's just focus on the spin up portion, the one that leads to the second analyzer. So the spin up portion, it's just this. So the input for the second analyzer is it's a spin up portion of the first analyzer, which, as we learned from the last video, can be represented as its components of spin. So 1 or square root 2 spin up in the x direction plus 1 or square root 2 spin down in the x direction. So given this as the input for the second analyzer, we see that the spin down of the particles that are recorded in the x analyzer were just counted into a separate branch, while the spin up portion for the x analyzer was fed directly to the third analyzer. So spin up in the x direction will be the input for the third analyzer. So let's put the input for second analyzer and input for third analyzer. And then again from last video, we saw that this could be represented as its components of spin. Since we have the input for the third analyzer, we can go on with finding the probability. Let's first find the probability of finding spin up in the z direction in the third analyzer. So as shown in the previous video, the matrix form of spin up in the x direction is just given as 1 over square root 2, 1 over square root 2, and then the spin up raw vector is just 1, 0. So going on with the inner product, we have so replacing these with these matrices, we get 1, 0 times 1 over square root 2. My bad. 1 over square root 2. So 1 multiplies with 1 over square root 2, which gives us 1 over square root 2 plus 0 multiplied by 1 over square root 2, which gives us 0. And then that just leaves us with 1 over square root 2 which is just equal to 1/2. So we see here that the probability of finding spin up in this case is just 1/2, which we see in the experiment. But why is the question? Well, for that, let's first analyze a slightly different version of the same experiment. So here is a slightly different experiment. Instead of having the spin down node connect to a counter, instead we have both the nodes connect to the third analyzer. And if we start the experiment, we see that this changes the results. We only get spin up particles for the z direction, for the third analyzer, my bad. And this makes perfect sense because all the particles originating from the first analyzer are spin up particles. So let's see why this uh, particular situation gave us a logical result, and the previous result gave us an odd result, I guess. So continuing on with the um, second experiment, we'll start off with the same process as the first. So the first output is the same, spin up in the z direction, but the output of the second analyzer changes. We find that it is the two beams spin up in the x direction and spin down in the x direction, combining in the third analyzer. So we know that half the particles coming from the x analyzer are spin up particles, and half of them are spin down particles. So using that information, we can determine the equation for the particles exiting the second analyzer. And we'll name this variable R. So let's find the probability of finding spin up for the third analyzer, given that the input is R. So let's represent R in its matrix form. To do that, let's just expand out this equation. So 1 over square root 2 times spin up in the x direction. As we previously have defined it, it is 1 over square root 2, 1 over square root 2, plus 1 over square root 2 spin down in the x direction, which we found in the last video to be 1 over square root 2, negative 1 over square root 2. So now multiplying the coefficients, we get 1 over 2, 1 over 2, plus 1 over 2, negative 1 over 2. And we get the final answer to be 1, 0. So by using the probability, we can find the probability of finding spin up in the third analyzer. So multiplying 1 with 1, we get 1. And 0 with 0, we get 0, so 1 plus 0 is equals 1. Square that, we just get 1. So we find the probability of finding spin up. Okay, right. So we find the probability of finding spin up in the final analyzer as 1, meaning that all particles um, coming into the third analyzer will always be spin up. And And another way to look at this is to look at the outputs of the second analyzer, which are just spin up, my bad, spin up in the x direction plus spin down in the x direction. But one thing must also be considered. Half of the electrons coming into the final analyzer are spin up in the x direction, and half of them are spin down in the x direction. So how do we properly convey that through this equation? So if we think back, 1 over square root 2 gives us the same probability as 50%, as we've seen in the previous demonstrations of the inner product. So by using this coefficient, we can accurately model what is happening in the experiment. So what is spin up in the x direction? As we have previously learned, it is just 1 over square root 2 spin up in the z direction plus 1 over square root 2 spin down in the z direction. Similarly, spin down in the x direction can be rewritten as 1 over square root 2 spin up in the z direction minus 1 over square root 2 spin down in the z direction. So adding these two up, we just get this 1 square root 2 on the outside multiplied by 1 square root 2 spin up in the z direction plus 1 square root 2 spin down in the z direction plus 1 square root 2 spin up in the z direction, it's a plus sign, my bad, minus 1 square root 2 spin down in the z direction. So now we see the spin downs cancel, and we are left with 1 square root 2 times 1 square root 2 in the z direction, spin up in the z direction, my bad, plus 1 square root 2 spin up in the z direction. Remember, this spin up in the z direction came from the spin up in the x direction, while this spin up in the z direction came from the spin down in the x direction. So now, completing this equation, we get 1 over square root 2 times 2 over square root 2 spin up in the z direction. And doing this multiplication, we get spin up in the z direction 2 over 2 times 2 in the square root, which simplifies to 2. And then we just get 2 over 2 in the z direction, spin up in the z direction, which just gives us the spin up ket vector in the z direction, which just shows that the only particles that are the outputs of the final analyzer are spin up in the z direction, as we've seen in the experiment. So now if you look at the first experiment, we have the input for the second analyzer as a spin up ket vector, which is made up of with the 1/2 1 over square root 2 spin up in the x direction plus 1 over square root 2 spin down in the x direction. But we see that the spin down in the x direction for the first experiment is just recorded onto a counter. So this goes to counter. While the spin up x direction goes to the third analyzer. And since only like half of the information that originally comprised of the spin up ket vector made it to the third analyzer, we can see why we get both spin up and spin down results for the results of the third analyzer. This experiment highlights a key concept in quantum mechanics, that a measurement can disturb the system. In this case, the measurement is just the counter, we are counting the number of spin down electrons in the x direction. And as we see by the results, that disturbs the system. We no longer have only spin up z direction particles that we would expect. This is because only half the information is making it to the z direction. The other half of the information is being used to count how many electrons are spin down. However, if we look at the second experiment, we see that we find all the particles that are coming into the z analyzer as being recorded as spin up. Well, this is because we don't know which path that the electrons are taking through the x analyzer since we're not taking any measurement. This way, the x analyzer doesn't disturb the system, and the spin up particles originating from the z analyzer continue to be spin up. And that concludes the video. Thank you. Please answer the questions after watching the video.